Good day, Engineer Vergara. My name is Jonas Habonillo, and I am with my group mates Roland Martinez and Bjorn De Los Santos to present our design for Phase 1, which is entitled Design of Quasi-Resonant Half-Bridge Converter for a 200-watt power supply. So, for the overview of this presentation, we will be going through chapters 1 to 5, which is the introduction, review of related studies, methodologies, conclusions, and recommendations. So, Chapter 1, Introduction. Half-bridge converters. Half-bridge converters are considered one of the basic topological standards in designing DC to DC converters for switch mode power supplies, or SMPS. They consist of two power switches that operate alternately to produce a square wave AC at the input of the power transformer and are subjected to a voltage stress equal to the input voltage. Popular choice of converters of up to a several hundred watts. It can also easily achieve high efficiency and allow high frequency operation using quasi-resonant techniques. Next, half-bridge converter applications. The applications may vary from switching mode power supplies to motor drives. It is widely used in high power application and better transformer utilization. They can also be seen in fuel cell systems, electric cars, uninterrupted power supplies, and battery charging. Next, gap of the previous study. Quasi-resonant half-bridge DC to DC converters. Most studies on this topology are designed using zero current switching, or ZCS. In ZCS, the transistor current is shaped by resonant network, which reduces the current to zero prior to turn-off to eliminate turn-off losses. ZCS QRCs can operate at relatively high frequencies. However, several limitations exist. The first is maximum switching frequency is limited to 1 to 2 MHz by the undesired capacitive turn-on loss. The second is the switching frequency for lighter loads is significantly reduced, resulting in lower crossover frequency and slower transient response. Next, statement of the problem. Using zero voltage switching or ZVS over zero current switching. Zero current switching technique used in offline high-frequency operation is limited to 2 MHz. During switching period, the switching loss is higher for ZCS at higher frequencies. Efficiency decreases when ZCS technique reaches low output power. At higher frequency applications, wide input voltage range causes higher radiated EMI at higher frequencies compared to ZVS. Proposed design project. Voltage-fed isolated quasi-resonant DC to DC half-bridge converter design. The design will involve the zero-voltage switching technique, intended to support power supplies rated at 200 watts. The design can take an input voltage range of 350 to 420 volts DC with a nominal input voltage of 397 volt DC. Output voltage is 12 volts DC with an efficiency of 97.5%. It is also operated by two power MOSFETs or active switches with resonant frequency of 2 MHz with a 50% duty cycle. Modulated frequency is between 1.5 MHz to 2.5 MHz. Objectives: to analyze the proposed configuration of the half-bridge converter. Second is to cover the limitations of ZCS technique such as higher frequency switching for offline power conversion using the ZVS technique. Significance of the design project. The proposed design project uses the application of the zero voltage switching technique which allows for, first, the reduced switching stresses and power losses at on-off state at a high frequency which will improve the overall efficiency. Second is reduced electromagnetic interference produced during the switching of electrical current at high frequency. The limitations of the design project. The quasi-resonant half-bridge converter is designed and simulated using Power Stage Designer tool, PSpice, and Tina Pro circuit simulation software. The design will have a power output of 200 watts. The primary side AC to DC rectification stage is not included in the design and will only receive a DC input voltage range. The design will only include the control circuit network, resonant tank network, and rectifier network. All results will be based on simulation. Chapter 2: Review of Related Studies. So the first one is Switched Mode Power Supply, or SMPS. SMPS uses higher switching frequencies, which replaces the bulky line frequency magnetics with smaller ones, which offer significant size and weight reductions. The efficiency and size of the SMPS depends on a suitable switching frequency. So next is the full resonance converter. Numerous resonant converter topologies all operate in a similar way, where a square wave or pulse of voltage or current produced by the power switches is applied to a resonant converter circuit. There are two basic types of full resonance converters. First is the series resonant converter, or SRC, and the parallel resonant converter, or PRC. So shown here are the two images of the SRC here on the left and the PRC here on the right. So the LR and CR components are connected in series in SRC in order to create a resonant tank, while in PRC, the LR and CR components are connected in parallel. So next is quasi-resonant converters. It works based on a resonant switching element such as MOSFET. When the MOSFET is switched on, it generates a resonant pulse. This pulse is then filtered by the output LC network like the traditional converters. QRC uses two techniques: zero current switching or zero voltage switching depending on the required application of the converter. Next is the half-bridge DC-DC converters. Half-bridge DC-DC converter is a type of Buck-derived isolated DC-DC converter that can supply a higher or lower output voltage and provides an electrical isolation via a center tap transformer. It can potentially yield a higher output power, up to 500 watts at a certain switching frequency, but more complex to design compared to the flyback or forward topologies. Next, quasi-resonant half-bridge topology. The half-bridge ZVS QRC topology has been chosen to demonstrate the feasibility of offline high-frequency operation. The converter is operated in half-wave mode to maintain zero voltage switching properties, and the load range is limited. Next, quasi-resonant techniques. There are two techniques. The first one is zero current switching, or ZCS. So by incorporating an LC resonance circuit, the current waveform of the switching device is forced to oscillate in a quasi-sinusoidal manner, therefore creating zero current switching conditions during both turn-on and turn-off instances. So shown in this figure is the half-bridge zero current switched quasi-resonant converter. So the second one is zero voltage switching, or ZVS. It is defined as conventional square wave power conversion during the switch's on time with resonant switching transitions. It utilizes a square wave pulse at a constant on-off time that is varied on its conversion frequency to maintain output voltage regulation. Shown in this figure is the half-bridge zero voltage switched quasi-resonant converter. So next is the half-wave mode. To implement half-wave mode in ZVS quasi-resonant converter, a diode is connected parallel but opposite in direction with the power switch MOSFET to provide reverse conduction capability. Next is the transformer design. The transformer turns ratio is derived by equating the circuit input and output volt-second products. A topology coefficient K is introduced which specifies the ratio of the maximum switching frequency to that of the resonant tank frequency. The recommended K-factor range is 4 to 10 for a resonant half-bridge converter. Next, MOSFET consideration. A higher resonant frequency requires a smaller resonant capacitance. Since the resonant capacitance is the output capacitance of the MOSFET, the choices for the value of C are limited. It can be observed that for devices with relatively high output capacitance, it is necessary to have a higher minimum primary current to accomplish zero voltage switching. If the resonant frequency is chosen at 2 MHz, the minimum primary current is 0.1 amperes for a 400 volt operation using IRF 710. Next is the resonant control circuit. The design of a resonant control circuit consists of an error amplifier, a variable frequency oscillator circuit, a pulse generator, a toggle flip-flop, a gating circuitry, and a MOSFET driver for zero voltage switching. Next is the compensation network type. A switch mode power supply is a type of power supply that uses switching elements to reduce heat dissipation, power consumption, and efficiency. It also regulates the output voltage against any changes in the input line or output load voltage. SMPS accomplishes this regulation with a feedback loop network which requires a compensation circuit that has an error amplifier with linear feedback. So next is the EMI consideration. The effect of electromagnetic interference has a great influence in the design of converters at the megahertz switching frequency region. It generates a higher order harmonic which leads to higher EMI due to sudden changes in current and voltage levels. So for Chapter 3 methodology, it will be discussed by my groupmate Roland Martinez. Thank you.
My name is Roland Martinez and I'm going to present to you the Chapter 3 methodologies of the Phase 1 design of a half-bridge quasi-resonant converter for a 200 watts power supply. So in this slide is the process flow shown using the conceptual framework on figure 5. The input is a high voltage DC with a range of 300 volts DC to 420 volts DC. And the process is a quasi-resonant conversion using the half-bridge quasi-resonant network with a zero voltage switching technique, and the output is a low voltage DC of around 12 volts and 16.67 amperes. So in this slide is the block diagram of the quasi-resonant half-bridge converter using the CVS technique. So you can see the voltage source with a 3 block networks of switching network, resonant tank network, rectifier, and the output load resistance. For the switching network, it is using a 2 power MOSFETs as the power switching elements, and the resonant tank circuit using the C1 and C2 capacitors and L. And the rectifier circuit is the LO and CO, and the load resistance is the RL. So the isolation is between the resonant tank circuit and rectifier circuit, and it is using a center tap transformer, and the turns ratio is computed and shown on the succeeding slides. So this is the principle of operation of the quasi-resonant half-bridge converter using CVS technique. You can see in the figure 7 the schematic diagram of the half-bridge quasi-resonant converter using LT-Spice. So the circuit diagram is shown where the resonant C1 and C2 is equal to C3 and C4 and C5. C1 and C2 represents the output capacitance of the MOSFET switches, whereas D1 and D2 represent the body diodes of the switches, and L or is the total resonant inductance. It consists of the transformer leakage inductance and external inductance, which can be added to increase the total value of L. So to simplify the analysis, it is assumed that the output filter inductance is sufficiently large to be approximated by a current source with a value equal to output current I0. The voltage drop across the conducting semiconductor switches is negligible, and the switching times of the transistors or the MOSFETs are 0, and the switches Q1 and Q2 are identical, so that C1, C2 and C is equal. So at the end of the conduction period of transistor Q1, the voltage across C1 is 0, whereas the voltage across C2 is equal to supply voltage, and the output current flows through the R1, and the primary current is I0 over N, where N is the transformer ratio. So vice versa for the C2, where the input is equal to the process of the preceding explanation. So for the design requirements or required parameters for the design, the converter's electrical specification are as follows. So the input voltage has a range of 350 volts to 420 volts DC, where the minimal input voltage is around 397 volts, and the rated output power is 200 watts. So the output voltage is 12 volts DC, and the rated output current is 16.67 amperes. The resonant switching frequency is 2000 kilohertz or 2 megahertz, and the switching frequency for the normal operation is between the range of 1.5 to 2.5 megahertz. So for the design considerations, the design procedure for an offline high frequency CVS QRC with primary side resonance assumes that the following input data are used, such as Vs min and Vs max, or the input voltage range. The Vout or Vo is equal to output voltage, and the Iout minimum and Iout maximum is the output current range, and the F conversion max is equal to twice the F switching maximum, which is equal to the maximum conversion frequency, and the Fs max or the maximum switching frequency, to calculate the theoretical values for the design of the phase 1 or the half-bridge converter. So knowing the input voltage range, the turns ratio of the transformer is determined by the maximum turns ratio in the equation 1. So where Dmin is the minimum duty cycle, and typically 0.7 to 0.9 duty cycle for a half-bridge converter. The resonant tank design is based on the equations 2, 3, and 4, and the first equation defines conditions for zero voltage switching, while the other two defines the characteristics, impedance, and the resonant frequency. Using equation 3 and 4, it is possible to determine the values for the resonant components C1, which is equal to C2 and C. And from here, you can also calculate the inductance. So according to the reference, for today's devices, the COSS is in the range of 35 to 500 picofarads at VDS is equal to 25 volts. So with lower values corresponding to high voltage devices, that will be greater than or equal to 200 volts, and consequently with a relatively high on resistance. The maximum primary current can be determined once the turns ratio is chosen using equation 5. So since the voltage across the non-conducting MOSFET switch is clamped at the supply voltage, the maximum drain to source voltage can be computed using equation 6. To obtain the widest possible load range, it is necessary to select MOSFETs with a current and voltage rating according to equation 5 and 6. And the smallest possible output capacitance, C sub OSS, is equal to the computed or design capacitance. The minimum conversion frequency occurs at low line and full load. So equation 7H shows the relationship between the minimum conversion frequency and the load of this half bridge converter. So the maximum value of the normalized load resistance at which zero voltage is achieved is given by the equation 9. And the minimum regulated output current is determined by the Rmax of the equation 10. And it occurs at the maximum conversion frequency for equation 11. For the design sample calculations, we use the preceding equations in design considerations, where the transformer turns ratio is calculated using the Nmax formula, and we get 14 turns, and that will be 14:1 turns ratio for the transformer. And the resonant tank components calculation is given in capacitance and inductance, where capacitance is equals to 23.6 nanofarad, and that will be equal to the C1 and C2, and of course the output capacitance for the half bridge converter. The same with the L, or the inductance for the leakage, and the magnetizing is equal to 1.33 microhenries, same as the output inductance. And the characteristic impedance calculation is given using the formula Z sub n is equal to 5.3 ohms. And the resonant frequency calculation is also computed, and that will be around 2.008 megahertz, or approximately equal to 2 megahertz. So for the experimental calculation results, we use the calculated values from the preceding slide to have a 200 watts half bridge CVS quasi-resonant converter operating with minimum input of 350 volts DC and maximum input of 420 volts DC, and a nominal input voltage of 397 volts DC, so that we can get a 12 volts DC output and 16.67 amperes rated output current. And the minimum conversion frequency of 200 megahertz was implemented on the phase 1 design. The compensation network we use is based on type 2 isolated compensation network with inner loop, and the experimental values are the same with the PWM and LLC counterpart. And the MOSFET gate driver or controller we use is the UCC 25600 of Texas Instruments, with a resonant mode controller integrated circuit designed for DC to DC conversion application. It implements high performance and frequency modulation control. So you can see the figure 8, or the typical configuration of the UCC 25600 for resonant converters.
This is the simulation of the design of quasi-resonant half-bridge converter for a 200 watts power supply. So as reference, we use the Power Stage Designer tool of Texas Instruments for the reference design using the PWM, or conventional topology of the half-bridge converter. So given the design parameters, we use the design values as the minimum input voltage of 350 volts and maximum input voltage of 420 volts, and the output voltage is 12 volts, and the output current is 16.67 amperes, and the switching frequency is 2 megahertz or 2000 kilohertz. So these design parameters is also used in the TINA Pro design or final design of the quasi-resonant half-bridge converter. So given the initial design parameters, using this Power Stage Designer tool, we get the recommended values for the transformer design, which is 12.40:1 turns ratio, and the transformer inductance is 117.17 microhenries, and the inductance of the transformer is 0.24 microhenries. So choosing the recommended values, we get the initial reference design of the half-bridge converter. So going to the loop calculator, we can see the plot of the total gain and total phase together with the gain power stage, phase power stage, gain error amplifier, and phase error amplifier. So here we use the minimum input voltage 350 volts and 12 volts, and we can get the other information for the control scheme, but we are going to use the voltage mode control buck converter since we are going to lessen the output voltage or convert the higher voltage to lower voltage output. So we are going to use a compensation network of type 2 with inner loop, and this is the design for the compensation network as reference. Then these are the component values that we are going to use for the final design in Tina Pro. So in here we can also see in the PWM or conventional topology of the half-bridge converter the initial output of the switching in MOSFET 1 or Q1 and Q2. So whenever the input voltage is increasing, the width of the plot is narrower than the lower input voltage. So proceeding to the final design of the quasi-resonant half-bridge converter for a 200 watts power supply, we are going to use the Tina Pro Cloud for the simulation and the schematic design of the quasi-resonant half-bridge converter for a 200 watts power supply. So here we are going to use an input voltage of 420 or the maximum input voltage. Then the parameters that we computed using the manual calculation or the theoretical values. So 23.6 nanofarads for the C1, C2, C5, C6, and C8. And also the inductance for the leakage inductance is 1.33 microhenry, and same with the output inductance is 1.33 microhenries. So now we are going to simulate the final design of the quasi-resonant half-bridge converter. So using the transient method or the transient simulation, we are going to use 200 microhenry since we are going to use 200 microseconds since this simulation will take a long time for the output to generate. In Tina Cloud Pro, we are going to use a smaller time scale. So zooming in the plot of the output of the half-bridge quasi-resonant converter with a zero voltage switching, we can see in the final output or the output current is around 16 to 20 amperes, and the output voltage is around 15 to 16 volts, and the switching voltage for the Q1 and Q2 is having a 0 voltage switching. If you zoom in a little bit more, we can see the difference between the switching of the power MOSFETs. So you can see that there is a gap between the switching time off and time off of the out B and the time on of the out A. So we can have a wider 0 voltage switching for the power MOSFETs. So again, this is the final design of the quasi-resonant half-bridge converter with 0 voltage switching using the UCC 25600 of the Texas Instrument for the 0 voltage switching resonant controller or the gate driver for the power MOSFETs. And this is the compensation network, which is a type 2 compensation network. And this is the half-bridge quasi-resonant converter for the 200 watts power supply.
My name is Bjorn De Los Santos, and I'm here to discuss chapters 4 and 5. Now for chapter 4, we have the conclusions of our study. The zero voltage switching or ZVS technique was implemented with the half-bridge converter configuration. The zero voltage switching techniques were discussed on this paper and employed on the design for a 200 watt SMPS with a 2 MHz switching frequency. The DC characteristics of the half-bridge ZVS QRC were analyzed based on the design procedures. For Chapter 5, we have the recommendations from our studies. For possible future developments of the QRC half-bridge converter design, further improvement should be done on the efficiency once implemented in the actual prototype. The zero voltage switching or ZVS technique can be improved at a higher switching frequency, and proficiency in simulation software can be used to determine the delimits occurred in this study. And so that is all for our report on our study involving the ZVS QRC half-bridge converter design. And thank you for listening.